All right. There we go. All right. So this is a brief run-up on antiderivatives and an explanation of them. So basically, what an antiderivative is the opposite of a derivative. You're essentially doing the opposite of it. So I'll start with that. So f prime of x. Well, actually, no, let's not start there. Let's say f of x is equal to x cubed. All right. So the derivative of f of x through the power rule is going to be equal to 3x squared. What an antiderivative is exactly that. It's an antiderivative. You're doing the opposite. Now he has a strange donation, a strange notation, I'll say here. He is saying that f prime is equal to the function f. So when he says f, he's looking for the antiderivative of said function f. Now, it's easier to just straight denote this in this fashion over here. This is the symbol for antiderivative right here. Really big S. Now, this means antiderivative, and we're going to say f prime of x dx. This is the notation you're more likely to see on the test. So let's say we want to find the antiderivative of 3x squared dx. Now, when you're taking the antiderivative, you're doing the opposite of what you did to take the derivative. So the power rule for taking a derivative is that you have x to the n, and when you take the derivative of that, you end up getting n x to the n minus 1. That's the regular derivative chain or power rule there. Now, like I said, antiderivative is the opposite of that. So when we take the antiderivative, what it's going to be equal to, if we take the antiderivative of n x to the n dx, this is going to be equal to n x to the n plus 1 divided by n plus 1. So whereas here you were pulling 1 to the front and then subtracting 1, here you're going to add 1, then divide by that. It's the exact opposite. So here, 3x squared, we're going to add 1 to the 2 to get x to the third, and then divide. So it's going to be 3x cubed over 3, which gets us back to x squared. Or x cubed, my bad. Gets us back to x cubed. So that's a brief overview of what an antiderivative is in respect to the power rule. So here you can see f is an antiderivative of smaller function f. I'm going to call this f of x to make it easier for notation. So we have that f prime is equal to f of x. So when it wants just straight f, it wants you to take the antiderivative of f of x. So it says that 1 over 3 x cubed is the antiderivative of x squared. This checks out because you add 1, then you divide by the new number. So that checks out. Same thing here. And then here's that notation I just said. I didn't even notice you put that there. But x to the n plus 1 divided by n plus 1, this is what the antiderivative is right there. Now, sines and cosines, you learned derivative of cosine is negative sine, derivative of negative sine, negative cosine, and derivative of negative cosine is sine. And the cycle repeats. Now you just got to learn that you got to go backwards. So if you want the derivative of sine x, it's cosine x. But if you want the antiderivative of sine x, it's negative cosine x. So this is going to be antiderivative, and this is just going to be derivative. moving on through the notes here. That's just a brief little overview there. See if he has anything weird. Ah, yes, I see. This is very confusing to look at. But here's what it's talking about. Basically, say you take f of x is equal to 3x squared plus 7. When you take the derivative, that 7 goes away. So you're left with 6x. For an antiderivative, when you take the antiderivative of 6x dx, you're left with 3x squared, but no constant. So we don't know whether or not this function had a constant. So we say, okay, so plus c being a constant that you can solve for later. But you have to put that plus c because you do not know whether or not there was a constant on that original function, which is what all this means. Don't forget your plus c. That's just for a constant that may have gone away when you took the initial derivative. Here are two separate rules that can be assessed. Say I'm taking the antiderivative of 6x to the fourth dx. Well, this is going to be gross to look at after I do all the other dividing stuff. So with this rule right here, c being a constant and f prime being the antiderivative, we can pull that 6 to the front and take the derivative of f to the fourth dx. Any constant you can move out to the front and it'll still give you the same answer. After we take the antiderivative here, we get that it's 6 times 1 over 5 x to the fifth dx. So we get 6 over 5 x to the fifth dx, which is what would have happened if we kept the 6 right there as well. It may not look like it's very useful now, but it does get useful when you have big numbers or do multiple antiderivatives in a row. The second rule is also very useful. If I have the antiderivative of 3x squared plus 5x plus x to the sixth, and they want me to take the derivative of all that, that's going to be messy to do that all at once. So what this says right here is that we can break it down into separate antiderivatives. So make this one plus 5x dx plus the antiderivative of x to the sixth dx. You can do all of them separately. So this one here is going to just be x to the third. This one here is going to be 5x squared over 2. And this one here is going to be x to the seventh over 7. Don't forget your plus c. I forgot it on the last one, I know. But here, you can just break it down instead of having to worry about what to do with that whole big thing. I know it's kind of hard to see over the words there. That's why I'm saying as well. So moving on down. Also, to f double prime is equal to x. Here's what he did here. He did multiple antiderivatives right here. So if we do what he said, we're going to say, okay, we have this f double prime of x, and we want to find f of x. So f double prime of x is equal to, let's make it different. No, let's use the same thing, sine of x. So we take our first antiderivative of x plus sine of x dx. So antiderivative of x is going to give us, that's x to the 1, so 2x squared over 2. And then what's derivative of sine x, or antiderivative of sine x? So negative cosine gives us positive sine, so this is going to be minus cosine x plus c. So there's our first antiderivative done. Now we're at f prime. This is f prime of x. We still have one more to go, so we're going to take the antiderivative of this as well. Also, if you have some random constant, say this was a 7, when you take the antiderivative, you're going to add an x to that. Because if you were to take the derivative of 7x, you're left with 7. Just a quick side part. So now when we take the antiderivative of this, we're going to get to the third over 6 minus sine x plus cx plus d. Now, c was our unknown constant. It became an unknown constant times the next after the next derivative. And we still had to add another variable just in case there was another constant that was unknown, denoted as d, which you can see he did right here. There's d, there's our cx. Okay, so a particle moves along a straight line, and we're given that v of t is equal to t plus 1. We're given that s of 0 is equal to 5, and we're asked to find s of t. Now, this is a definite. We are going to find the c value here. So, we're given that v of t is equal to t plus 1. And we know that s of t, so you got s of t is, pretty sure that's direction, or it's been a minute since I've done this. I'm going to just say s of t. It's either distance or that other d word. I can't remember. But the derivative of this is velocity, v of t, and the derivative of this is acceleration, a of t. So we're given v of t, and we need to find s of t, so we can plug that number in. So take the antiderivative of t plus 1. We get t squared over 2 plus t, and this is equal to s of t. And then we're given the initial condition that when t is 0, s of t is 5. Oh, almost forgot. Right here, that's a plus c. You can't forget the plus c. And using this initial condition, we're going to actually solve for c. So we plug in 0, we got 0 squared divided by 2 plus 0 plus c is equal to 5. So zeros go away, we get that c is equal to 5, which means, coming over here, that our overall equation is s of t is equal to t squared over 2 plus t plus c. All right, going on down. So this is another initial, this is another one just like we just did, only this time you're going from acceleration to velocity. So you have sine of t plus t, and you're also given you're given velocity, and I'm just going to call that distance, velocity and distance. So you're actually going to solve for c, and you're going to solve for d. So first, antiderivative, we're starting at acceleration, a of t. So we're going to get, okay, that's going to be negative cosine of t plus t squared over 2 plus c, and this is equal to v of t. And we're given our initial condition that when t is 0, v is 7, or v of t is 7, so 7 is going to be equal, cosine of 0 is 1, so it's going to be negative 1 plus 0 plus c, so c is going to equal 8. So that we have that v of t is equal to negative cosine of t plus t squared over 2 plus 8. So now we're going to come over here, and we're going to take the antiderivative of v of t, which is going to give us s of t, which is equal to negative sine t cubed over 6 plus, coming down here, plus 8t plus d, our additional variable I talked about earlier. Then we're given the second additional condition. When t is 0, s of t is 12. So we have that 12 is going to be equal to 0 plus 0 plus 0 plus d. So d equals 12. And that gives you the same answer he got here. Your overall equation for s of t is negative sine of t plus t cubed over 6 plus 8t plus 12. Oh my gosh. Riemann sum. Okay. So basically, what a Riemann sum is an approximation of area of a curve where f of x is continuous. So we're going to come down here and, oh, no, what in the world did he, whoa. Okay, I'm going to try my best to decipher this. Oh, he's going over properties. Also, introduced by Riemann sum up here is what's called an evaluation integral. So you're going to have the antiderivative, but also you're going to be given a certain range, like say from 2 to 3. So say I want to know how much what the area of x squared dx is from 2 to 3. So I'm going to take the antiderivative, and I'm going to get that x cubed over 3. And then I'm going to go from 2 to 3. Now what you do is going to be, you're going to plug in 3 for x minus 2 for x. And this is going to give you some value. That you will use. And that's why he has your interval here. He has a to b, which is why your integral is a to b. So this is just a general overview of properties that he has here. So this is the property we talked about earlier, where if you have two functions added to each other, you can split them into two separate integrals. If you have a constant on the inside, you can move it to the outside. And also, what in the world is this here? A to b of c dx is equal to c times b minus a. Oh, that's a constant. The integral of a constant is equal to the integral minus itself. Okay, yes, this makes sense. So say we have the integral of 2 to 3 of 7 dx. So we're going to have 7x from 2 to 3. So it's going to be 7 times 3 minus 7 times 2. We can use a little property here and get 7, 3 minus 2. Because this is going to be what? This is going to be 7 times 3, 21 minus 14. That gives us 7. Here, it's going to be 7 times 1, which is still going to be 7. Same thing. And lastly, we have the integral from a to c of f of x dx plus the integral from c to b of f of x dx is the same as the integral from a to b of f of x dx. And this makes sense. If we have an interval here, we're going from a to c, then c to b. So a to c, c to b. If we take the integral at these two separate points, integral, and then we add those two integrals together, it's going to give us the total over this entire area. Man, this was a long one for you guys. All right, yes. So here we go. He's doing a left endpoint, midpoint, right endpoint, refer to the points at the f of x. All right. Oh yeah, this is the first time I looked at this, by the way, guys. All right. So what are you told? So n is equal to 3, and he does not tell you which one to use. Okay, I see. He uses right endpoint here. So basically, with a Riemann sum, you're drawing rectangles. So we'd say, okay, we got a rectangle here, and a rectangle here. That's what n equals 3 means. It means you have 3 rectangles. So Rn, this is right Riemann sum, is going to be equal to the right point values. We have a right point here. That's a right corner, and right corner. All right. And we're given that our function is x squared on the interval 0 to 1. All right. I'm still trying to see what in the world he did there. 3 squared plus 2 over 3 squared plus 1. Alexa, stop. Plus 1 times 1 over 3 and the like. Wow. What an excellent comment. Okay. I may have to move further down until he gives me an actual equation because I can't actually remember how to do Riemann's sum. And he does not give an equation. Wow, he just jumped straight to it. Okay, so these are partial sums, which are Riemann sums. Is evaluated. You give an x squared. 1 over squared, if you had a 1 over x squared, and that would just be 1. So from what I can tell here, what he did actually is probably going to be, no, I'm not going to do it like that. I'm going to wait till I find the formula. I may come back to that in a moment after I found the formula. Here we go. Comparison of intervals. If f of x is greater than or equal to 0, then the integral, or the antiderivative from a to b of f of x dx is greater than or equal to 0. If f is greater than or equal to g, then the same is true about the antiderivatives. And if f is in the center of an interval, then on the same interval from a to b, it will still be in the center. My goodness. Okay, so here's what he did here. So you're given an interval from 8. 8 is less than or equal to x cubed, which is less than or equal to 27. So, just like he did up here, it's going to be m times b minus a times big M times b minus a, which doesn't really look like he did. But, oh, that's not 0.1, that's times 1. Okay, that makes much more sense. So yeah, it's going to be 8 times b minus a, which is going to be 3 minus 2, is going to be less than or equal to the integral from 2 to 3 of x cubed dx, which is less than or equal to 27 times 3 minus 2. That's what he did there. Comparison of intervals. Okay, so fundamental theorem of calculus is a big one. And it can be confusing, but it's actually quite simple. All right. Let's see if he has an example down here. All right. Okay. Wow. I'm sorry. Okay, so basically fundamental theorem of calculus. You have that big F of x is equal to some interval from a to some kind of x. We're just going to use x here. F of t dt. When you take the antiderivative of this and you plug in the values, you get that big F of x is simply, or f prime, because to get rid, oh yes, now I remember now. So you want to get rid of the antiderivative, you take the derivative. Since an antiderivative is the opposite derivative, they cancel each other out. But you simply got to plug this x value in for t. So f prime of x is equal to f of x. Simple as that. And if you have some sort of like x squared up top, you're going to, I can't remember. I'm sorry. I'll come back to it. I will. But here it's talking about that once again. It's saying that for an interval of f of t from a to b, it's going to be the same as big F of b minus big F of a, which is true because we just saw the same thing. If f of x, if big F of x is equal to the integral of f of t on some interval a to b, then it would have to be true that this is true because they're the same thing. Because you're going to end up taking this and then solving for f of a minus f of b. All right, so this is just a few examples of the derivatives that I was talking about. So he did the integral from 2 to 3 of x cubed dx. So you take the antiderivative here, and you get that x to the 4th over 4. Also, this is what's referred to, I know I didn't say it earlier, as a definite integral. A definite integral is an integral that is on an interval. An indefinite is one that you simply solve for x, and that is the only time you include a plus c. If you're given an interval to work upon, then there is no plus c. Please remember that. From 2 to 3. So we're going to plug that in. 3 to the 4th is 81 over 4 minus 2 to the 4th is 16 over 4. So we got 81 over 4 minus 4, which is going to give us, like it says up here, 16 and 1/4. And here's an interesting one here. So this is a cool one. 0 to 2 pi of sine of x dx. And this is going to be equal, and you can say this, due to symmetry. And here's the reason why. So sines and cosines both cycle along the axis, going the same amount up and down as they go along. So they're going to have the same area above as they do below. I know this is an accurate drawing, but apologize for that. So, just like he shows here, plus and minus. As long as you're going on complete cycles, it will always be equal to 0, which was proven right here. Cosine of 2 pi is 1, so it's going to be -1. Minus 0 is 1, -1. So it's going to be -1 plus 1. It's going to equal 0. Or you can just straight up look at this and say, okay, so it's going to be 0 due to symmetry. Oh, that's it for this one. Let's move on to the other one. Let's see how much is here. 3, 4, 5, 6, 7. Oh boy, there's still quite a few. All right, so here's the continuation. Now this is a new one. This is an FTC one. Fundamental theorem of calculus. So as we can see here, you have function x on top, all these t's down here. All you simply do is you plug in all the x's for the t's, and then just say by FTC, fundamental theorem of calculus, f prime of x is equal to this. Once again, if f of x is equal to an antiderivative and you take the derivative, it cancels out that antiderivative. The only thing you have to do is sub the t's for the x's. It has to be in terms of x because big F of x is in terms of x. All right. Right down here, the average value of a function. Now, he did this in two different ways. He did it in fundamental theorem of calculus format, but I'm just going to do it in regular format. Say I have an interval from 4 to 6 of 3x squared dx. And I want to know the average value. The formula for this is going to be 1 over b minus a times integral a b of the function dx. And that's just what he did here. He showed by a fundamental theorem of calculus. We talked about, since f of x is equal to an antiderivative, that simply having this interval is the same thing. But it's a lot easier to look at it this way. So our interval is going to be 1 over 6 minus 4, which is just going to be 1/2 times the integral from 4 to 6 of 3x squared dx. So we take our antiderivative, we get it as 1/2 times. And once again, this is why that constant pull outside of the antiderivative rule is so useful, because we could have had 1/2 in this and make everything not look pretty, but we can keep it outside until we're completely done taking the derivative. It's going to be x cubed from 4 to 6. So it's going to be 6 to the third minus 4 to the third. And that's going to give us 152. That looks like an 8. 152. And that was our answer for this part, but we still have that 1/2 times 152, which is going to give us 76. And this is our average value of the function on that interval. All right, so this is an example of the mean value theorem. The area under F is equal to the area of the rectangle of height F average, and there exists a value C in the interval A to B such that the average is equal to F of C. And this is an indefinite integral. Like I said, this will have a plus C attached to it. It is not definite. But the mean value theorem, once again, it states if we have a graph with some squiggly function here, we're going to call this B, we're going to call this A. I know he has it written right there, but I'm going to do it in my own way. And we're going to call this rectangle here, and that top line here, we're going to call that actually g of x. All right, because f average looks like tave, and I don't want to keep saying tave or f average. So by mean value theorem, you have to write that. There exists a value c where f of c is equal to g of x. All right. Oh, and you have to put on a to b, the interval a to b. And then you're able to get that done. So moving on down. Substitution. Okay, U-sub. U-sub is an excellent tool. I'm in Cal 3 and I'm still using U-sub. So basically what U-substitution is, you have a function that looks like this, just like he did. We're going to say integral of x squared square root of 1 plus x cubed dx. How do you take the derivative of this? You can't. It's weird. So you use something called U-sub. You say, okay, I have a u that's going to be equal to 1 plus x cubed, and then you're going to take the derivative, du. And this is going to be equal to 3x squared dx. So now, what do we have left in the function? The function looks like this right now. We have x squared times the square root of u. So we need to get just an x squared on this side. Oh, there's dx here too. So we can get rid of that x squared and dx. So we're going to divide by 3, and we're going to get 1/3 of du is equal to x squared dx. So now we can sub it in. When we sub it in, we have u to the 1/2. This is still u square root of u. I just changed it, du. By saying that 1/3, and see what I did? It's 1/3 du, moved it to the front because you can do that. We said that u is equal to 1 plus x cubed, which allowed us to put it under that square root. And then we said that 1/3 of du is equal to x squared dx, which allowed us to pull that out. Left with a simple function we can take the antiderivative of. So we take the antiderivative of u to the 1/2. We're going to get that it's 2/3 u to the 3/2. All right. Oh, I forgot about that. Excuse me. No more antiderivative because we just took it. So we're going to multiply that out. We get that 2/9 u to the 1/2 plus c. And the last thing we have to do is we have to plug our u back in. Our u being 1 plus 3. That's a 3/2, sorry. 1 plus x cubed. So our final answer is going to be, I'm just going to come over here where I can write. It's going to be 2/9 of 1 plus x cubed to the 3/2 plus c. And that's how you do u sub. Here he's still going through on the u sub, looking at it. And here he did another example where u instead was in the cosine, but it's still the same premise. Wow, he took up a lot of room for these guys. My goodness. But yeah, that's going to conclude this. If you guys have any questions, hit up Miranda Reeves, and she'll get you in touch with me. You guys have a great day.